Hello everyone, this is our final presentation for ME 401. We are Composite Axle Bond Strength by Kyle Hayes, Gio Cerruti, and Jack Lotempio. Some background on our project is that we're attempting to make the axles lighter for Clarkson's FSAE car. Usually these axles are made out of steel, but for this project we are attempting to use composite tubes with steel inserts to adapt CV joint tripods. The main goal of this is to test the adhesive bond between steel inserts and carbon tubes, and we were planning on testing circular and hexagonal shaped tubes, applying both torsional load until the bond breaks.
All right, to manufacture our prototypes, we scaled down the full-size carbon tube axle to a smaller test piece so that to lower our costs and make it easier to test. And the way we did this was by machining some inserts that would mimic the real inserts that would go on the car, but at a smaller size. And we bonded them to these carbon tubes using the epoxy adhesive that we selected. We also had another type of adhesive, but we didn't test as many of those. And we used microspheres mixed with the epoxy to make sure that we had a constant, correct adhesive layer thickness.
So for our experimental test plan, the first step was to determine the tube and adhesive joint size. To do this, we used strength of material torsional stress calculations to make sure that the adhesive bond breaks before the tube, since this is the overall goal of the entire experiment. After that, specimens then were assembled with manufacturer recommendations of adhesive conditions in mind. And for the test jig, we created a test jig that would hold the test specimen securely, and then we'd be able to apply a moment to the test specimens using a moment arm. So for the test procedure, the first step is to secure the test jig to a stable table. For this, we use the jig table in the Formula Workshop. After this, the test specimens are then secured inside this jig. The moment arm is attached to the other side of the jig, and then a bucket is attached to the end of this moment arm. Sand can then be added to the bucket until the specimen fails. After this, you should measure the weight of the bucket. Using this and the length of the moment arm, you can calculate how much torque is applied to the specimen from the weight of the bucket. Then record the data into a table. Repeat these steps 2 through 8 for all the specimens, and then after this, the data can be analyzed.
In these pictures, you can see our test setup. You can see the test jig fully assembled with the moment arm and test piece installed on it in the left photo. And in the right photo, you can see the bucket that we use to add torque to our system.
For our results on the left-hand side, you can see our theoretical max torque and failure points of each of the tubes. For the circular tube, it was about 420 foot-pounds. This comes out to a shear stress of about 4,300 on the adhesive bond. The failure point for this was the adhesive joint. Yet again, the goal of this was for the adhesive joint to break before the tube. For the hexagonal tube, we expected it to be greater than the circular tube, just because due to the nature of the geometry of the hexagonal tube, the adhesive joint isn't purely under shear stress, it's also under compression and tension. This comes out to about the same 4,300 psi on the adhesive joint, and the estimated failure point was the adhesive joint. When we look at our experimental max torque loads, we can see that the circular tube came out to 60 foot-pounds and about 1200 psi, but unfortunately these tubes broke at these specimens broke at the tube most of the time, meaning that this was inconclusive data. Same for the hexagonal tube, an increased torque load of about 110 foot-pounds coming out to 2200 psi on the adhesive bond, and these also broke at the tube. It's estimated that the hexagonal tube had a greater torque load, not because of the geometry of the adhesive bond, but because those tubes were actually a little bit thicker just because they were what we were able to buy easily.